Welcome to this technical walkthrough regarding Folks Finance Liquid Staking Audit Competition. We're delighted to have Gidon from their team hosting this session. It will guide us through the core functionalities of their code base, shedding light on their smart contract assets while sharing valuable insights. From the Immunefi side, I'm Daniel, and I'll be co-hosting alongside Folks Finance technical expert. But without further ado, I'll hand it over to you, Gidon, who will lead us through the technical details.
Great, thank you, Daniel. I'm going to share my screen now. Hopefully this works. Okay, can you see this?
Yes.
Okay, so thank you. So I'm here to introduce the Folks Finance Liquid Staking Protocol. So what this protocol is a high level, it allows users to participate in Algorand consensus by delegating the algo stake to Folks Finance. So typically, if a user wanted to participate in Algorand consensus, they would have to run their own Algorand node, but we would run their Algorand node on behalf of the users at Folks instead, so they don't need to worry about any of these complexities with running nodes. And in return as well, we also give them a liquid staking token, which they can then use throughout the ecosystem. So you should be able to access all the links I go through in the Boost page. So the first link that I want to talk about is the Google Doc we shared, which gives you an overview of the design of the protocol. So the background to this is that Algorand used to not incentivize consensus. Instead, they saw it as a thing that users should do regardless of incentives. But recently, they've decided to switch over and start rewarding users that participated in Algorand consensus. And alongside this, there's this transition where they were giving governance awards before, but now all those awards are now being delegated to consensus. So this liquid staking protocol we had used to run on the governance program, and we upgraded it to support the new consensus protocol. So if we look at the technical background here, so the Algorand Foundation released a white paper, which gives you an overview of how Algorand consensus will look like. It's scheduled to release in about a month's time. So the idea is that the protocol will be ready on day one of the launch of the incentives. So to participate in Algorand consensus, what you need to do is you need to have at least 30,000 algo and register the participation keys inside an Algorand node. So not only can this be prohibitive to small users that don't have 30,000 algo, but it could also be prohibitive to people that are not so tech savvy that they know about running Algorand nodes. And as well as you have to worry about managing the infrastructure to make sure that your Algorand node stays live and is participating throughout, because otherwise you can be kicked out of consensus. There's also some other interesting quirks when it comes to Algorand consensus. One is that they also set a maximum cap on the amount of algo you could have and participate in Algorand consensus with. And this is to prevent centralization risks, where if an Algorand node that had a lot of stake said that we're participating in consensus, but in reality their node was down for whatever reason, then that could potentially stall the network. So therefore, Algorand sets a cap on the maximum algo you can participate in consensus with, and that I think is set to 70 million algo. So that's a brief overview of the different details about Algorand consensus. Another interesting thing as well is that when you participate in consensus, you issue the transactions to register yourself online and offline. This doesn't come into effect immediately. Instead, you have to wait 320 rounds for the change to take effect. So if you say that you're coming online in round 5,000, let's say, then the account will only start participating in round 5,320. And similarly, this also applies to changes in stake. So if an account had 50,000 algo, and then you received an additional 10,000 algo, then for the next 320 rounds, the network is thinking that you're just participating in consensus with the 50,000 original algo. And then only 320 rounds later does it credit the additional 10,000 algo, and now that you're participating with 60,000 algo. So that's also one consideration that we need to keep in mind when reviewing the liquid staking protocol. So if we move on to the protocol itself, so we have an XALGO token, and this XALGO token is the liquid staking token. So when users stake their algo and give it to Folks Finance, in return, they receive XALGO. And XALGO is an interest-bearing token, so its value continually increases as consensus rewards are earned. Initially, the rate of minting algo to XALGO is 1-to-1. So if you gave 100 algo, you would get 100 XALGO. But as the rewards accumulate, the rate will also change. So maybe that when you go to burn the 100 XALGO you originally got, you're going to receive 110 algo because you earned 10 algo in rewards. Now, if the user wanted to mint XALGO again, they would have to send 110 algo to receive 100 XALGO. So the XALGO continually increases in price relative to algo. And because of the delayed effects that we spoke about earlier, one consideration we need to make is that when we decide the rates to convert algo to XALGO, we need to consider what rewards are going to be earned. So the simplest approach is that you just take the ratio of the amount of algo that is being staked and the amount of XALGO that is circulating. So if there's 100 XALGO circulating and 200 algo being staked, then you know the rate is 2-to-1. However, this could mean that large changes in stake affect the amount of rewards that are going to be earned in the next 320 rounds. So if I were to, let's say, mint algo and I receive XALGO immediately, I will start earning the rewards for the XALGO immediately. However, my stake isn't actually participating for another 320 rounds. So in effect, you are earning other people's rewards, which you shouldn't be entitled to. And the comparable case of when burning, you receive the algo immediately, and you will be losing out on the rewards for the next 320 rounds. So these effects partially cancel out each other, but there could be scenarios where the difference between the two is exaggerated. So maybe some user could take advantage of this and earn more rewards than they should. So therefore, when we do the immediate minting of XALGO, we don't exactly give you the rate, but we give you a slightly lower amount. And that amount is determined by what we think the rewards will be earned in 320 rounds. So we'll see those formulas quite shortly. So the other thing we earlier spoke about was about how the algo balance in these accounts can be maximum 70 million algo. And because of this, and we want to be able to support more than 70 million algo inside our protocol. Therefore, we divide the algo being staked among multiple different accounts, and we call these accounts proposers. They're called proposers because they are proposing new blocks to the Algorand network. So therefore, when someone mints their algo, the algo is split between all the various proposers. So if you were to send 100 algo and there's 2 proposers, then 50 algo would go to each proposer. It doesn't work exactly like that, but we'll see inside the code how this approximately evaluates to something like that. In terms of fees, we take a 10% fee of all the rewards earned, and you can review these formulas in your own time. So like I mentioned before about the amount of XALGO you receive when you mint, we consider a premium which makes sure that you can't game the system and earn other people's rewards within the 320 rounds. So that's factored in this case where we multiply the rates by 1 minus the premium. We also offer the ability to get the exact rate you want by delaying the XALGO you receive for 320 rounds. So in which case, we wouldn't multiply by 1 minus premium, we would just give you the XALGO 320 rounds later, and it completely nullifies the delayed effects that we spoke about. When it comes to burning, we just also immediately give you the algo received, and you will just forfeit the rewards earned over the next 320 rounds. And that is split between all the other stakers. Since the smart contract is already deployed and we're upgrading it, therefore we need to consider the current state of the smart contract. Because when you upgrade a smart contract, the state of the smart contract persists between updates. So if we want to make changes to the state, then we need to decide what state we want to keep, what state we want to remove, and maybe some state that we want to update. So over here, we list all the various states that already exist in the smart contract and the ones that we'll be removing, adding, or changing. So I won't go through all of these, but you can see, for example, that we used to have a global state variable called initialized, which indicates if the smart contract was initialized, and we're changing it to be this init variable. That is just to make it easier to do future upgrades, but we'll see that inside when we look at the repository. We also have a list of all the various operations that is available in the smart contract. So we follow the Algorand ABI. So this may be similar to what you've seen in other ecosystems, if you're familiar with Ethereum, where we specify all the various methods available, give a description of them, list their parameters, and the types that they return. So if you want to look into the operations that we support and a description of them, then I would say this is the best place to look. So if we move over now to the repository. So the repository contains a README, which gives you all the instructions to get started, compiling the smart contract as well as running the tests. So you'll need one thing in particular, which is the goal CLI tool. So the way you get the goal CLI tool is you need to use an Algorand node. So you need to install an Algorand node, and you can follow the instructions on the Algorand developer page here to install it on whichever operating system that you use. So once you've installed the Algorand nodes and you have their goal CLI available, then you should be able to just run these simple commands to install the various packages you need in Python and npm. And then lastly, you should be able to run the tests simply by either running npm run test or running this command here. So I'm going to change the screen I'm sharing. Okay, so this should be the repository. I've just cloned it locally, so it's easier to go through it. So the first thing here to look at is we have the old global state of the smart contract. So this is the global state of the smart contract that we currently have before it's being upgraded. So this state persists between updates, so we need to modify this. So here we have it as reference what the old global state is. And this is in the file consensus state v1. So what we're interested in is the new state, which is consensus state v2. And if you compare the two together, state 1 to v1 to state v2, you'll see they're practically the same, just with a few minor differences. So if we move over to the smart contract, So the first thing we do once we upgrade the smart contract from V1 to V2, my computer's running a bit slow. Just closing a few applications. Hopefully that should speed things up. Okay, so I'm just scrolling up to the initialize method. Okay, should be here. So we see here the initialize method. So this is the first method that is called, and it should only be called once. And what this does is that it ensures the transition between the V1 and V2. So we see that we delete the old initialize key, which we defined here with the bytes initialized, and we're replacing it with the new initialize key, which is init here. So that's the one modification we saw in the Google Doc. As well as that, we're also deleting the min proposer balance. So no more are we checking that the proposers have a minimum 30,000 algo. Instead, we just assume that this would always be the case inside the smart contract. And also one thing that we're introducing as well is the XGov admin, which we will speak about later on. So this is the transition from consensus V1 to consensus V2. Now, once we've initialized the smart contract, we can move on to the various methods that it provides. So if we look at some of the privilege operations first, so the admin, in this case, we have a number of different admins. One of these admins is the register admin, and the register admin is able to call this add proposer method. So what this does is that it adds another account that can hold algo stake. So each proposer can have a maximum of 70 million algo, or maybe a bit less than that. And then, so that we can support additional algo being staked, we have the ability to add multiple proposers. So if we had, let's say, 60 million algo staked and one proposer, we'd need to add a second proposer so that we had the capacity to allow more algo to be staked. So in that case, the admin would call this add proposer method and would make sure that a proposer was being added to increase the capacity that we have. And what this does is that it makes sure the proposer is rekeyed to the smart contract. So this gives control of the Algorand account to the smart contract so that it could send algo from the proposer itself and not rely on the proposer to sign the transactions. The next thing as well we do is that we store the new proposer in the state of the smart contract. So we use box storage in this case, which is just a way you can store information in Algorand. And when we do this as well, we ensure with this assert that we haven't already added the proposer. So we can't add the same proposer multiple times. So this was a bug that was reported in the previous order that we had, that we weren't checking this. So now once we've added a proposer, we need to actually participate in consensus with this proposer. So the way we do this is that we call the set proposer admin method. And this allows another Algorand account to issue the necessary transactions to register the proposer online, offline for consensus. So depending on who the caller of this is, affects the implementation it uses. So the first time you call this, in that case, we immediately set the proposer admin. So we would say the caller has to be the register admin, and then we check that there's the length of the box. In this case, this tells us whether an existing proposer is present or not. If there's no value in here, then this would evaluate to 0, and 0 is equivalent of false. And we would get into this case where the sender is the register admin and there's no existing proposer admin, in which case we set the new proposer with the immediate effect where it comes live at the current timestamp. If there already exists existing proposer, then there is a time delay of 24 hours before the new proposer comes into effect. And this is just to reduce any centralization risks, where users are aware of changes that are going to be coming into effect, and they can review that before it comes into effect. And if the proposer admin is the one who is updating itself, then they're able to do this immediately because it's just the same user updating their own admin. So there's no need for a time delay there. So now that we've set a proposer admin, we could issue the transactions to register online or offline in consensus. So to register online, we would call this register online method. It requires an algo payment as well. And this algo payment will be used as the fee to issue the key registration transaction. So to be eligible for rewards in Algorand, when you register online, you need to pay a 2 algo fee. And potentially this algo fee may change, so we don't validate the amounts of algo that you are sending. Instead, we just assume that the caller will pass in the correct amount. If they don't, then just rewards won't be earned, but they could just reissue another key registration to override that. We also validate, like I said, that we have the proposer admin is the one that's calling the transaction. And one thing as well is that we don't, at Folks, we don't want to be the ones that necessarily run all the different nodes. We want to be able to delegate the node running to other stakeholders within the ecosystem to improve the decentralization of the protocol. So therefore, the proposer admin may not necessarily be Folks Finance. It could be another project within the Algorand ecosystem. So when it comes to registering offline, it's slightly different, where it could be the proposer admin that is registering them offline, or alternatively, it could be Folks Finance, and that is the register admin. And this is because in cases of bad behavior by the external node runner, we are able to forcibly remove the M from the smart contract from running the consensus nodes on our behalf. But again, we don't want to be able to immediately take over with no delay, because then that increases the centralization issues. So therefore, we can forcibly remove them, but we can't add our own for another 24 hours. And it's for that reason. So those are the register online and offline methods. I think my computer's frozen again. Okay, it's back. One other thing as well is that we want to be able to participate in XGov. So XGov is a program that Algorand runs, which gives you the power to vote on which proposals to fund within Algorand. And the power that you have when it comes to votes is determined by the amount of blocks that you propose in the Algorand network. So since we'll be proposing many blocks through the delegated algo, we want to be able to support XGov. So these two, this method, subscribe XGov, allows us to subscribe to the XGov program. And the way it's done is we just internally call the XGov registry application with the necessary parameters. And we specify another account, which is the voting address, which can vote on behalf of the proposer. So the voting address is passed as a parameter, and this will be able to vote in XGov. So we don't need to issue the necessary transactions from the proposer to vote in XGov. Instead, the voting address can handle all of that. Only the smart contract needs to worry about subscribing to XGov. There are a number of other privileged operations we have when it comes to just updating states. These are fairly straightforward, so I'll just run through them quickly. So one of them is to update the admin. So we have various different admins, and they can update them. They can update each other with different access control rules. So the admin, which is like the super admin, it can update any of the other admins. We have the register admin, which can update itself, and the XGov admin, which can update itself. We also have the ability to upgrade the smart contract. Again, this is done with a 24-hour time delay to reduce centralization risks, so users could burn their XALGO before the updates came into effect if they were not happy about it. So the schedule update smart contract schedules the updates to happen in 24 hours, and then the update smart contract method would confirm the update. So you see here that we're making sure that the timestamp has passed before we can actually finalize the update. Moving on to the other admin operations, we have an update of a max proposer balance. So this ensures the proposer balance doesn't exceed the threshold needed to be eligible for rewards. So our grant set this to 70 million. So we will set our own proposer max balance to be below this, maybe 65 million or so. And this is to ensure that rewards that we earn don't push us over the limit. So if we have 65 million limit and the actual limit is 70 million, we have a 5 million capacity of rewards, and we'll make sure that we claim these rewards before we get anywhere close to the 70 million threshold. We have the ability to update the fee. So this is the fee, that the percentage that we take of the consensus rewards. And then we can also claim the fee. And we'll see this, we'll move back to this later on. If we move over to the user operations, we'll start with the immediate mint. So this allows you to stake the algo and immediately receive XALGO. So when you do this, the first thing we do is we check that you send the algo to the smart contract. So this is what we're doing here when we have the check algo sent. And we're checking the receiver is the current smart contract address. Once we receive the algo, and we're sure we received it inside the smart contract, we need to distribute that algo between all the proposers, because we want to make sure that the algo is balanced between the proposers. So we don't want a proposer which has 10 million algo and one which has 50 million algo, because then it increases the centralization issues, because one proposer going down could have a larger impact than if it were to be split evenly between the proposers. In addition, if some of the proposals are being run by third parties, we don't want to have any way where you can manipulate the algo between the proposers. So you could say, I want this third party to be staking my algo entirely, and then not be split between all the various parties. Instead, we want it to be evenly split between all the different proposers. So this is what we do when we call this receive algo to proposers subroutine. So we have the algo right now inside a smart contract, and we want to distribute it across all the different proposers. So the way we do this is that we take the current balance between all the different proposers over here, and we save this to a variable called total balance. So if we had a proposer that had, if I can write some comments here. So like proposer 0, 5 million, and proposer 1, 5 million. The total balance in this case will be 10 million because it would be the sum of all the proposer balances. So we say total balance 10 million. Now, we're having a user that is staking an additional, so a user is staking 1 million algo. In this case, we want the target to be the amount of algo each proposer should have after the user has done this stake. So we're doing the total balance plus the amount that is being staked. So it's 10 million plus the 1 million, which is 11 million. We're dividing it by the number of proposers. So by 2. So it's, oops. So it's 10 plus 1 divided by 2, which is equal to 5.5. So we want to have 5.5 million algo in each proposer. So this becomes our target. We are actually also adding 1 here, and that is just to round up in case the user is staking, let's say 3. Therefore, we want to be able to distribute, we want to make sure that we fully distribute the algo that they're staking. So we would allocate like 2 to one proposer and 1 to the other. So that's the reason why we have this +1 here. So it's not going to be an exact split in the case of an even number, but it's roughly equivalent because it's only +1 micro algo, which is very small in the grand scheme of things. The next thing we do is we ensure that the max proposer balance isn't exceeded. So we know that the new proposer balances will be 5.5 million. So if 5.5 million is below the max proposer balance, then we're fine and we can proceed. In this case, it would be fine. Then we have this for loop which splits the algo between all the different proposers. So we'll go through this in stages. So the first thing we do is we read what is the current proposer balance of the first proposer. So in this case, we would read that the proposer balance is 5 million. Then we would say what is the difference between the target, 5.5 million, and the current balance, 5 million. And the value that it allocates is 500,000. And that is this value here, target minus proposer balance. And then we know that is the value that we should send from the smart contract to the proposer. So we would do 5.5 million minus 5 million, which is 500,000. And then we send 500,000 algo from the smart contract to the proposer. And then we repeat this process for each proposer until we fully allocated all the algo among them. Now, there could be the case where if we modify this, and let's say somehow we were in a state where proposer 0 had 7 million and proposer 1 had 3 million. Maybe because proposer 0 has accumulated lots of rewards and no one has done any operations. In this case, we want to get closer to an even balance between these two proposers. So we would instead, in this calculation, and actually as well here, the user is staking still 1 million and the target remains at 5.5 million because the total balance is 10 million. So if we do this calculation again, we would see that the target minus the proposer balance in this case, or we would fail in this case because proposer balance is less than the target. So we would skip the allocating any algo to the first proposer. And then in the second proposer, we would allocate the algo to them entirely. So we'll see that the target will be 5.5 million. And then the proposer balance right now would be 3 million. So that would evaluate to 2.5 million. But then we're taking the minimum of 2.5 and then how much algo we have to allocate between all the proposers, in which case that's 1 million. So the minimum of 2.5 and 1 million is 1 million. So we're allocating all the 1 million algo that the user is staking to the second proposer. So the new updated balance will be 7 million algo for the first proposer, remaining the same, and 4 million algo to the proposer 1. So this is an overview of how the algo is being split between the various proposers. Just my laptop again is frozen. Okay, I'm back. So if we go back to the immediate mint. So now that we've allocated the algo between the various proposers, we need to send the XALGO that the users owed to them. The way we do this is that we need to calculate what the new rate is. Before we calculate what the new rate is, though, we need to update some variables inside the smart contract. So we have this subroutine called update total rewards and unclaimed fees. And what this does is it just takes what the old balance was across the proposers, what the new balance is, and assumes the difference between the two is all the rewards that we earned. So if there used to be 100 algo in the pool, now there's 101 algo, we know we've received 1 algo in rewards. In that case, then, we will just update some global state variables to say that a percentage of this 1 algo that we earned should be reserved for the protocol as a fee. So that's what we're doing here. Once we've done this update, now we can finally calculate the ratio of algo to XALGO and send the XALGO to the user. So that's what we're doing here in this case, where we're calculating, given the amount of algo staked, adding in as well the rewards that have been earned, subtracting the algo sent, because that shouldn't be considered in the rate, because this is the algo that the user is sending right now. So we should discard that. And using that, we can calculate what the amount of XALGO they should receive by multiplying the algo sent. So if they're staking like 10 algo, then we multiply it by the amount of XALGO in supply and dividing by the amount of algo. And then, since there's an immediate mint as well, we're diminishing the amount slightly by considering the premium, because you're earning other people's rewards for 320 rounds. So that's what we're doing here. And now, once we've done that, we can finally send the XALGO to the user with the amounts that we calculated. And that's what we're doing here on line 691. So that's the immediate mint. Let's move over to delayed mints when my computer responds. Okay, so the delayed mint is very similar, but instead of calculating the amount of XALGO that you should receive, we simply store in a box how much algo you sent. Now, after 320 rounds, which we're saving right here in the box, you'll be able to claim the delayed mint. So everything else up to this point is the same, except that we don't send the XALGO to the user, we defer it to be sent later. So the next step after calling delayed mint is 320 rounds later, you can call the claim delayed mint and receive the XALGO. So the claim delay mint is the second half, and we're calculating the rate at the time when you are claiming. So this means that you didn't earn the rewards for the 320 rounds, but instead you're going to get the true value of the conversion between ALGO and XALGO at that current time. So we're not considering the premium in this case. So that's the claim delayed mint. As well, the claim delayed mint doesn't necessarily have to be called by the person who did the original delayed mint transaction. Instead, you could call it on behalf of another user, and in return, you get a small algo payment as an incentive for doing that. So this way, we can provide a better user experience where the user doesn't need to come back 15 minutes later to do another operation. Instead, another party would automatically ensure the XALGO is sent to the user for them. Now, if we move over to the burn operation, so this is similar to the mint operation, except it's the opposite, where you send the XALGO to the smart contract, and the smart contract needs to distribute the algo from the proposers to the user. So we have this method, which we call send algo from proposers. And if we take the example where we'll write another example here, where let's say, again, proposer 0 had 5 million, proposer 1 had 5 million as well, and the total balance is 10 million. Sorry, my computer's very slow. Okay. So now, in this example, the user is unstaking 1 million algo. So the first calculation we do is we calculate what the target is. So the target is the amount of algo we expect each proposer to have after we've done the unstaking. So this is just the opposite of the minting. So we would have a total balance of 10 million. We're subtracted by the amount that they're unstaking, in which case this is 1 million. We're divided by the number of proposers, in which case this is 2. So we have the target of 4.5 million algo. So if we see 500,000 algo should be sent from each proposer. So we do the calculations where we loop through all the different proposers and we try to send algo from it. So we see the proposer balance of 5 million is greater than the target of 4.5 million. So we're going to be sending some algo from that proposer. We next calculate how much algo to send, in which case it's going to be 5 million minus 500,000, or sorry, 5 million minus 4.5 million, which is 500,000. And then we will send 500,000 algo from the proposer to the smart contract. And at the very end, once we've sent all the algo from the proposer to the smart contract sends the total amount from itself to the user. So that's what we're doing at the very end here. If we change the proposer amounts again, so that the first proposer had 3 million and the second had 7 million, the target would remain at 4.5 million, but the algo being sent would be sent from different proposers. So we would do this if condition for the first proposer, and we would see the proposer balance of 3 million is not greater than the target of 4.5 million. So we're not going to be sending any algo from that address. We would reach the second proposer, or proposer 1, which has 7 million algo, and that is greater than 4.5 million. So we're going to be sending algo from that. we take the proposer balance, which is 7 million, subtract it from the target, 4.5 million, which is 2.5 million. And then we take the minimum of 2.5 million and the remaining amount to allocate. So, which is 1 million algo, which is the amount that's unstaking. So the minimum of 2.5 million and 1 million is 1 million. So we know we're sending 1 million from proposer 1. So the updated balances will be 3 million from proposer 0 and 6 million from proposer 1. So just the same as the minting, but the opposite. So this is the burning. The last thing to talk about in the smart contract is that Algorand has resource limitations. So you can't read the balances of unlimited addresses when you do a call to a smart contract. Instead, you can read the balances of four accounts for each smart contract call you do. So this could lead to an issue where if you have more than 4 proposers, we don't have the ability to access all their balances and send algo to and from those addresses. Therefore, we add an additional method here, which we just call dummy. And we're able to call this method to increase the allocation of accounts that we can access later on inside the smart contract. So if we had 8 proposers, then we would do a dummy call to give us access to 4 of them, plus the other call, the smart contract, which would give us an additional 4. And that would cover the 8 proposers. And theoretically, we can scale to as many as 30 proposers, in which case we would need 7 dummy calls. In terms of testing, I recommend you look through the different test cases we've written. So what the test does is that it creates a private network for you. It deploys and sets up the smart contract and runs various checks on the different methods. So if you want to write your own tests as well and check the behavior, then you can just quite easily do so by adding the tests after the smart contract has already been created. So that's everything, I think.
Thanks, Gidon. Thanks for this comprehensive walkthrough. Before wrapping up, let's highlight some key takeaways to help our security researcher effectively identify vulnerabilities. So the first question I have is, have there been any unexpected bugs in past audits for this particular protocol, and how did they affect your security assumptions or threat model?
Yeah, so we had one previous audit for an earlier version of the smart contract, and it was related to centralization risks. So one thing we did after this is that we reviewed the smart contract entirely and made sure to reduce the centralization risk as much as possible. So this involves adding delays to operations, to some admin operations, as well as making sure we can't update fees to be greater than certain values, and overall just making sure that the user has the ability to respond to any changes that we make. Otherwise, in past audits, generally the vulnerabilities that are reported to us are logic flaws where we're failing to validate certain behavior. So just making sure we have enough test coverage to ensure that we are checking the behavior is correct.
Great, I see. And which areas should bug hunters prioritize in your code base, and why?
So I think the most important part of the code base is the calculations for the amount of XALGO to receive when staking in the immediate mint and claim delayed mint methods. And similarly, the amount of algo to receive when unstaking in the burn method. In addition, the splitting of the algo between the proposers and making sure that they should be equally split between them. And then lastly, just the general access controls, making sure the admin operations can only be done by the appropriate accounts, as well as the fact that you can't claim someone else's delayed mint.
Great. Would you have any tips or best practices for finding vulnerabilities in the system?
Yeah, I think to look at the tests and then try to modify them and see how it responds. I think that would be the easiest way to go about things, as well as just reviewing the calculations, seeing whether it matches what's written in documentation and whether those calculations make sense. And also writing tests that try to break the access control. So sending writing tests where the transactions are sent by accounts which shouldn't have the appropriate privileges to call those operations, and seeing whether it succeeds or fails.
Great, thank you. And what resources would you recommend for understanding your project and its code base in depth? I see that you've shown in the first part of this presentation a white paper and like a descriptive document, but feel free to elaborate it more.
Yeah, I think the documentation that we went through is probably the best bet to start with. Otherwise, I think looking at the code directly, because maybe the documentation says one thing, but the code does something else. So ultimately, the code is what matters. So making sure that everything is correct there. One other thing as well, which is interesting, is that the smart contracts are written in the language called Python, and the ABI types, which are like the typing you can use to help writing background methods, they may not be entirely enforced in the compiled TL code. So if you look at you compile the smart contract and you get the TL code, you could see, for example, that specifying an array type of fixed length doesn't actually check the length. So therefore, as well, it'll be interesting to review the TL code itself and making sure that there's things that aren't missed, which we thought would be included inside the compiled TL code, which impact the security of the smart contract.
Nice. That's very interesting and useful. Can you elaborate on the various access control roles within your within this protocol?
Yeah, so we have 4 admins. So 3 of them are in global state. So that is the global state key admin, which is sort of viewed as the super admin. So it can claim fees, as well as update the other admins. So then we have the register admin, which can add proposers, set the proposer admin, sometimes with a delay if one has already been added before. And it can also register a proposer offline forcibly. And then we have the XGov admin, which can subscribe and unsubscribe from the Ireland Foundation XGov program. Then lastly, each proposer has its own admin in box storage, which is the proposer admin, which can register a proposer online and offline.
Excellent. Which part of your code base do you expect to be most challenging for security researchers, and where might bugs arise due to implementation complexity? You said it earlier that the most not challenging, but the part that you would like Audit to prioritize is the calculation part, but do they coincide?
Yeah, so there's a couple different areas, I think, probably, which maybe the calculations are the most challenging to review because they're quite simple calculations, but making sure they're done correctly is still extremely important. In terms of what would be more challenging, I would say the consideration that this is an update to an existing smart contract, which is already deployed. So you need to consider the current state of the smart contract that is already there, and which of these state variables will persist and which are changing, and making sure they switch over between the two is good. As well as what I mentioned earlier about the compilation of the PyTL codes to TL code, and making sure that there's no issues in the compilation where we're assuming some check is being done, but it's being missed when it actually gets compiled down to the lower level language.
Fantastic. Thank you. Thank you so much, Gidon, also for sharing your expertise. The session was packed with valuable insights and technical details, a fantastic opportunity for us all. If you have follow-up questions, feel free to reach out to Fox Finance team. They're more than happy to assist via the designated Discord channel called Fox Liquid Staking Audit Composition. And lastly, a quick reminder, Fox Finance Liquid Staking is currently hosting an audit competition on Immunefi, a unique event with $30,000 reward pool up for grabs. And you have time until December 19th. For more details about this program, visit immunefi.com/audit competitions and check out their program. Again, for any clarifications, reach out to Fox Finance team on Discord. And once again, thank you all and happy hunting.
Thank you, Daniel.